Thank you. So the next portion of our panel, as people come back in, our morning is Professor Andy Lo from MIT. He will be speaking today. Warning: physics envy may be hazardous to your wealth. We're happy to have Andy back at the annual conference. He was here, I think, a couple of years ago, the same day we had Jim Simons. Andy's also an IFE Senior Fellow, and so we're always welcome when our fellows come and join us. So with that, I will hand it over to Andy. Quick housekeeping note: we're going to run for about an hour and 10 minutes. Also, if you want to ask questions, we've actually activated the microphones. So when we get to the Q&A session, push the button in front of you, ask your question, and make sure to turn that off afterward. And with that, I'll hand it over. Thank you.
I'd like to start by thanking David Jaffe and the IAFE for inviting me to speak to all of you today, for Goldman Sachs for hosting the event, and all of you for attending. It's a particular pleasure and privilege for me to be on the same program with Dick Roll, this year's IFE SunGard Financial Engineer of the Year. Dick's been an inspiration to a lot of us in academics, and so it's really an honor to be part of his event. As David said, the title of my talk is a somewhat provocative one, and it corresponds to a paper that I co-authored recently with a colleague of mine, Mark Mueller, who is a former physicist as well as a portfolio manager, and now retired and doing physics again, except for when he talks to me, in which case we do a little finance. And the topic has to do with a peculiar psychological disorder that most economists, including myself, we suffer from. And the psychological disorder is physics envy. We all wish that we had 3 laws that could explain 99% of all behavior the way the physicists do. In fact, as you know, we have 99 laws that explain maybe 3% of that behavior. And it's terribly frustrating for us. And so this is an aspect that I'd like to talk about, because obviously the theme of today's conference and a lot of the discussions have been on the financial crisis, and in particular the role of models and in particular quants in that crisis. So I'm not going to focus on that specifically. Obviously there are many talks both before and after that will cover it. What I'd like to take up in the next half hour or so is a broader issue about the way economists, and that includes financial economists, the way we approach modeling and the implications for decisions that are made both in industry and in government. And so I want to state at the outset that I'm not a physicist, but one of the reasons that Mark and I collaborated was because we both had somewhat different perspectives. As many of you know, in fact, how many of you have a physics background in the audience? Raise your hand. I just want to know how many people I may offend by the end of this. And I won't offend you on purpose, trust me. But the comments that I'm going to make really are designed to try to contrast physics with finance, and to do it in a somewhat honest and substantive way, as opposed to philosophically or religiously, and to try to take out of that some interesting lessons that we might all benefit from. And so in collaborating with Mark, who, as I've mentioned, is a physicist, I learned a few things. The first thing that I learned was that there is a hierarchy even in physics in terms of respect or street cred, as they say. That at the very top of that pecking order are the string theorists. By the way, Mark is a string theorist, I should say. And they're, for reasons that I'm sure those of you in physics know, that's an extraordinarily challenging field, and you really have to have a very broad range of talents. And I'm going to argue that finance is the string theory of economics, in the sense that you require a broad array of skills, far broader than any part of economics. But I'm getting a little ahead of myself. We'll get into this in a little while. I'd like to start with a bit of a socio-historical background as to why it is that economists have physics envy. And it has to do with just one person. Physics envy all started with a fellow by the name of Paul Anthony Samuelson. Paul Samuelson, as many of you know, was a great economist at MIT who recently passed away. In 1947, Samuelson published his PhD dissertation. And the PhD dissertation was modestly titled Foundations of Economic Analysis. Now, this is a graduate student, remember, who titled his thesis Foundations of Economic Analysis. And the interesting thing is that it was modest because, in fact, it did become the foundations of modern economic analysis. And in 1998, Samuelson wrote an essay in the Journal of Economic Literature that gave us some insight into how he came to write this incredible dissertation. And so let me just quote from that article. Perhaps the most relevant of all for the genesis of foundations, Edwin Bidwell Wilson was at Harvard. Wilson was the great Willard Gibbs' last and essentially only protege at Yale. He was a mathematician, a mathematical physicist, a mathematical statistician, a mathematical economist, a polymath who had done first-class work in many fields of the natural and social sciences. I was perhaps his only disciple. I was vaccinated early to understand that economics and physics could share the same formal mathematical theorems, Euler's theorem on homogeneous functions, Weierstrass's theorem on constrained maxima, Jacobi determinant identities, underlying Le Chatelier reactions, etc., while still not resting on the same empirical foundations and certainties. In other words, Samuelson was saying in this passage that his idea early on was to pattern economics after physics. And this program that was started in 1947 took on enormous momentum, excuse the physical reference, and ended up changing the very face of the field to the point where breakthroughs like utility theory, general equilibrium theory, game theory, rational expectations, option pricing theory, and efficient markets all grew out of that literature, out of that tradition. It's really quite stunning. And as you all know, the efficient markets hypothesis underlies virtually everything we do, the idea that prices fully reflect all available information. Now, since we're here at Goldman Sachs, I can't resist telling a short anecdote about efficient markets and Goldman Sachs. As many of you know, Fisher Black was a faculty member at MIT for many years, but then subsequently decided to join Goldman. And a year after he got to Goldman, I remember a conversation that one of my friends who worked here had with Fisher about what he thought he was accomplishing, given that he was one of the staunchest supporters of efficient markets, certainly when they were both at MIT. This is a former PhD student of ours. And Fisher summed it up very nicely. He said that markets look a lot more efficient from the banks of the Charles than they do from the banks of the Hudson. And I think that summarizes where things ultimately ended up. As many of you know, the efficient markets hypothesis is simply not supported by the data. In some work that Craig McKinley and I did years ago, we rejected the random walk hypothesis, and with a variety of different psychological and behavioral evidence that has been brought to bear, not the least of which is the current financial crisis, it seems that at least the basic premises of efficient markets has been called into question. Now, Dick is going to have a really interesting perspective this afternoon, so I encourage you all to take careful notes, because there is an alternative explanation that does not necessarily rely purely on bad behavior or any kind of behavior, and it's certainly worth sorting through all the issues. But the question is, how do we reconcile this idea of a physical approach to economic phenomenon, which has been terribly successful, certainly from the academic perspective, all the achievements that many Nobel Prizes have been awarded for, versus the realities of markets that many of you deal with in industry? That's really the focus of my comments. So I want to point out that even Paul Samuelson had reservations about his particular research program. This is really a stunning passage that comes right out of his dissertation in 1947. Only the smallest fraction of economics economic writings, theoretical and applied, has been concerned with the derivation of operationally meaningful theorems. In part, at least, this has been the result of the bad methodological preconceptions that economic laws, deduced from a priori assumptions, possessed rigor and validity independently of any empirical human behavior. But only a very few economists have gone so far as this. The majority would have been glad to enunciate meaningful theorems if any had occurred to them. That's pretty cold. In fact, the literature abounds with false generalization. This is an incredibly prescient passage that could actually apply to economics today, but it was written in 1947 by the person who started us down this road of the mathematization of finance, of physics envy. And so what I'd like to do is to try to come up with some insights into how we grapple with these two mutually inconsistent perspectives. The fact that mathematics is a critical component of what we do now in economics and finance, but that what we're trying to capture really isn't all that mathematizable, certainly in every circumstance. So to do that, let me give you a very simple psychological illustration of the potential breakdown of some of the principles of efficient markets. And I think all of you have seen this in one form or another, but I think it's kind of an instructive experiment. We're going to engage in a very simple game here. I wish we could do it for real, but I've been told by Human Subject Committee members that I'm not allowed to actually do this. And you'll see why in a minute. Suppose that I've got a hypothetical urn, and in this urn has 100 balls, 50 of them red, 50 of them black, but otherwise identical in every other respect. And we're going to play a very simple game. I'm going to ask you to pick a color, red or black, and don't tell me what it is, just write it down on a piece of paper. And then I'm going to pick a ball out of this urn, and if I pick the ball of your choice, you win $10,000. But if I don't, you win nothing. Okay? And you're going to get to play this game exactly once. And so the questions that I want to put to you are, number one, what color would you prefer? Anybody have a preference? You're shaking your head. Why not? Why no preference? Meaningless. Why is it meaningless?
Because the name of the color is not what's important. It's the fact that I picked whatever it is.
Sure, but I mean, which color would you prefer, red or black? The choice. Does it matter? No, because there are 50 red balls and 50 black balls, 50-50, right? So it shouldn't matter. Second question, how much would you pay me to play this once? Now, that's a harder question, and this gets to your personal risk preferences, right? There's no right or wrong answer here. So let's figure out how much you'd pay. And this is why I want to do this for real, but again, I've been told I'm not allowed to. How many people would be willing to pay $1 to play this with me once?
What's your credit worthiness?
Good point. I could tell we're in a new world, aren't we? Man. How about if I get a credit default swap, to...
No, I wouldn't pay $1.
You wouldn't, okay. All right. Apart from credit issues, how many people pay $1? $1,000, $2,000, $3,000, $4,000, $49.99, $5,001. Okay, so $5,000 looked like it was the market clearing price. Now, how did you get that number? Exactly, the expected value, right? It's $10,000 or zero, 50-50 probability, and this is all a highly quantitative audience, so you're able to calculate the expected value. Okay, now let me try something else out on you. We're going to play the exact same game, but this time with a different urn. Now, this urn contains 100 balls, red and or black, but I'm not going to tell you the proportion. Okay? Everything else is identical. Now, the same two questions. What color would you prefer? Anybody? Red. By the way, it turns out that in the general population, there is a slight preference for red over black. So that proves my point. Anybody else have a different choice? Black, okay. Does it matter? Why doesn't it matter? Well, you don't have any information, but on the other hand, I have the information, exactly. I choose the distribution, absolutely. So you pick black. Anybody else have a different perspective? The thing is that I have the information that there's a slight bias in red. So now you know I have that information. And I know you have that information. And you know I know you know. So how does that work then? If we do the infinite regress, actually it turns out that it's the same game. Yeah.
Same game. You would lose if you did it.
Yeah. It's the same game, or is it? Now, well, let's see. Let's see the second question and see how people.
How much would it cost to find out from you what the distribution?
Well, let's see. Let's see how much it would cost. How many people would play this game with me exactly once for $1? $1,000. $2,000. $3,000. So let the record show that we have far fewer hands at 3,000 than before. Okay, make it 4,000. $49.99. You would pay the same. You would. Why would you pay the same?
Because you don't know what color I prefer before you set up
Right.
the portion.
I don't know what color you would prefer, except that I do know there's a general tendency for a slight preference for red, but you know that, and we each know that we know that. So you don't think it matters. So you pay the same. Most everybody else here would not.
I'd do the same because you're going to make it 50-50.
How would I make it 50-50?
You're rational, otherwise you're going to lose.
How is that?
Because it's 50-50, you know, if you make it other than 50-50,
Yep,
there's a chance you're adding your risk. You don't want the risk, you're the house.
right. So that's a very interesting logic that you're looking into my mind and trying to figure out what I'm going to
You're
do.
a rational person.
Yeah.
You're the casino.
So it turns out that if we don't know anything about each other, if we have no information about each other, there's a very deep principle in statistics. Do we have any statisticians in the audience? Okay, so check to see, if I'm saying this properly. There's a very deep theorem in statistics known as the principle of insufficient reason. And this deep theorem, you know what it says? It says if we don't have any reason to think that it's anything else, it's 50-50. That's it. That's the theorem. In fact, if you don't believe that, let's just enumerate all the possibilities. It could be 100 red balls and 0 black balls. It could be 99 red balls and 1 black ball. It could be 98 red balls, 2 black balls, and so on. And if you go through all those possibilities and you equally weight them, you know what you get? You get 50-50. Now, when you explain this to people, and then you ask them how much they're willing to pay, the answer almost to an individual is, I will pay less for this. And when you ask them why, they'll say, well, very simple. In the first case, I know what my risks are. But in this case, I don't. There's uncertainty about the risks. Now, with most dictionaries and thesauruses, risk and uncertainty are considered synonyms. But here, we see that there's some kind of a subtle distinction, don't we? And in fact, this is a distinction that was made by an economist by the name of Frank Knight in 1921, not because of this. This wasn't developed until the 50s and 60s by Daniel Ellsberg, the famous psychiatrist and Pentagon Papers academic. This is known as the Ellsberg paradox. And the point of the Ellsberg paradox is that there seem to be layers of preferences for different kinds of randomness. And so Frank Knight argued that there are two kinds of randomness in particular. There's risk, which is the kind of randomness that can be parameterized. You know what the odds are exactly. And the other kind of randomness he called uncertainty, the kind that you cannot parameterize, all the other kinds of randomness. And the reason he made this rather academic distinction is actually motivated by industry. He was trying to explain the outrageous profits that these so-called robber barons were able to generate in their day. And he just couldn't believe that it would be appropriate from an economic perspective for any one individual to have so much money. You know, Bill Gates is worth something like, what, $40 billion, depending on the price of Microsoft. Does it make sense? Is it fair that any one person should have that much money? That just seems wrong. This is probably not the right crowd for me to be pitching that. But how can you explain it? How can you explain it in the context of rational economic theory? And Frank Knight said, the way you explain it is to acknowledge that risk, the kind of randomness that we can parameterize, ends up leading to businesses that have relatively minimal excess profits. That because the risks are so well understood, we can actually construct extraordinarily fine models to take advantage of them, and then the profits get competed away because they become eventually commoditized. A good example is, say, property and casualty insurance. That's not a business that I would suggest any of you quit your day jobs to try to start at this point, because the profits are pretty tight in that business. It's very competitive, and the risks of P&C insurance are pretty well understood. Not to say that there isn't innovation going on. It's a highly competitive industry, and people are always looking for that little tiny edge. Or life insurance is another example. Recently, I had occasion to look at my life insurance policy, and being interested in the underlying theory of life insurance and mortality tables, I made the mistake of digging deeper, trying to understand what goes on behind it, and came to the really depressing conclusion that if you answer 20 questions on a typical life insurance survey, they can actually forecast your time of death to within plus or minus 5 years. I mean, that's really depressing. Do you really want to know when you die? That's an example of, TMI, right? Too much information. But the point is that that's risk. We know a lot about mortality. We know a lot about property and casualty. We know a lot about certain things, and that's called risk. On the other hand, if you're an entrepreneur that takes on not risk, but takes on uncertainty, that's a whole different game. And there, the profits can be extraordinary simply because it's a relatively rare breed that is willing to expose themselves to the total unknown. Why? Because of the many different forms of fear that humans are subject to, the most potent form of fear, the deepest kind of fear, the fear that will stop you dead in your tracks, is fear of the unknown, as it should. Because what you don't know certainly can kill you. And that's hardwired into all of our cognitive faculties. And so for somebody to say, I'm going to quit my job, despite the fact that I've got 3 kids and a wife that wants to make sure that we have enough to provide for them, I don't care, I'm going to quit, and I'm going to basically take this on and engage in this incredibly uncertain business. You can imagine why it is that untold profits can arise in those kinds of situations. And so really this was the basis of Knight's distinction between risk and uncertainty. Risk, normal profits. Uncertainty, extraordinary profits. And it doesn't mean that it's easy, because obviously by the nature of uncertainty, we don't know. There are many internet multi-million, even billionaires that were born during the internet era. But there are also many, many more that basically went out of business. And so that's the kind of thing that's virtually impossible to parameterize. That's uncertainty. That's not risk. Okay? An example of current uncertainty is what's going to happen in various different technologically based industries like nanotechnology. MIT recently created a nanotechnology lab. I walked by it a few weeks ago. Amazing, beautiful, it was huge. And I had to say I was a little bit puzzled. Why did they need all that much space if it's about nanotechnology? I thought that they should give them 1 million square nanometers, and that should be enough. But no, they got a lot more. But the point is that, do any of you know whether or not that's going to be a viable business to invest in? What's the track record of nanotechnology? Well, there is none. And so how do you know whether or not that's profitable? Well, you don't. So how do you get entrepreneurs to get engaged? They're willing to take on uncertainty. Now, what Mark and I wanted to do in our paper was to take this idea and apply it a little bit more broadly, not just to trying to explain profits, but to try to explain various different approaches to risk management. And so what we do is to propose a slight modification of Knight's dichotomy of risk and uncertainty. And what we'd like to do is to create a taxonomy of uncertainty that contains slightly more refined gradations. And we came up with 5 that we'd like to describe. The 5 levels of uncertainty, in our view, ought to be defined in this way. Level 1 is complete certainty. So 2 + 2 = 4, no matter what day of the week it is, no matter where you calculate it, no matter how you do the math. Level 2 is Frank Knight's definition of risk. That's the 50 red balls and 50 black balls. Complete understanding of the randomness, totally parameterizable. That's risk. Level 3 is slightly different from level 2 in the sense that it's not risk, but it's fully reducible to risk, meaning if you have enough data, if you have enough analysis, if you have computational power, you can reduce something to full risk and no uncertainty. Okay? Level 4 is partially reducible uncertainty. What this means is that part of your system or model can actually be reduced to risk, but there's a component of it that cannot. And now this gets into economics and the rest of the social sciences. And finally, level 5 is complete and utter irreducible uncertainty. This is the kind of randomness that we will never be able to understand with our models. Okay? Now, the idea behind these 5 levels of uncertainty is that they require different methods for analyzing them. And so I'd like to take it out for a spin and apply this to a particular situation. In the paper, we apply it to do 2 different situations. One is a financial context, equity market neutral trading strategies. So I urge you to look at that for those of you who are interested. It's pretty elementary, but it highlights all of the various different levels of uncertainty in that very practical context. But rather than do that today, what I'd like to do is actually to take this and apply it to a physical context, just to really make clear that physics and finance are not so different in terms of their ultimate objectives, but they are different in the kinds of risk and uncertainty that characterize the phenomenon. So I'm going to apologize in advance if I offend the sensibilities of any of the physicists in the audience, and feel free to speak up and argue against these points. But it's a very simple approach that we take in the paper. We're going to apply this 5 levels of uncertainty to the simplest physical system that we can describe in the next 5 or 10 minutes, which is the harmonic oscillator, the good old-fashioned spring. Most of you, I think, have taken high school physics, and if you did, you'll have gone through this calculation of Hooke's law, right, for the spring, where you've got a block resting on a frictionless surface attached to a spring, and at rest, the idea is that the spring is doing nothing to the block, but when you pull the block away from the wall, the spring exerts a force exactly opposite to the direction that you've pulled it, and in direct proportion to the displacement from its resting point. And so Hooke's law, as all of you will remember, is the force exerted by the spring is minus k times x. X is the displacement, and k is the spring constant. Now, right here, I want to make a point, which is that this simple law is probably more successful, has a better fit than any economic theory that we've ever been able to come up with since the history of the beginning of economics. That's pretty depressing, if you ask me. Because, if you think about how Hooke came up with this law, I mean, I got to tell you, it doesn't seem brilliant, frankly, because this is the first thing I would have tried. And it worked. It worked so well that this is the basis of an extraordinary number of physical systems. And it's really remarkable how well it works. You get R squareds of 99.9998 versus the kinds of R squareds we get in economics, which is sort of like 1 minus that. It's really depressing. Now let me take this a little bit further and tell you where I'm going with this. So when you take Hooke's law and you marry it to Newton's F equal ma, you get a second order ordinary differential equation, which if you solve, you can show that you get oscillatory motion. The position x is going to be given by a cosine omega t plus phi, and given the appropriate parameters, you have perfect certainty about where this block will be at any point in time. So at t equal 3.5, we know that the displacement will be 1.7224. Level 1, perfect certainty, right? And again, even in reality, this is an extraordinarily good approximation. Now, let's add a little bit of friction into the system here. And I don't literally mean friction, but I mean measurement error. And let's suppose that we actually don't measure the displacement properly, but we measure it with some IID, normal 0 sigma squared measurement error. This is a system that I would argue is characterized by level 2 uncertainty. It's risk. We know exactly what the parameters are of the randomness. So therefore, at t equal 3.5, we don't know its displacement, but we do know that with probability 5%, it's going to be between 1.4284 and 2.0164, right? That's level 2 uncertainty. Now, what about level 3 uncertainty? Well, suppose we don't know that the error is normally distributed. Well, even though we don't know it's normally distributed, as long as we know that it's mean zero and that it's serially uncorrelated, then we know from the central limit theorem that the particular parameters don't really matter, and we can actually estimate them. And with enough data, we can actually quantify all of the risks that we need to. So this is fully reducible uncertainty. It's not risk, but it can be reduced to risk with enough data and with the appropriate sampling techniques. So to give you an example, suppose we simulated the results of this system and we did a standard fast Fourier transform. What we get is a single peak where that identifies the frequency of this particular spring. And even if we add more noise into the system, so the bottom graph is the displacement, the realized displacement, where the signal to noise ratio is 1 to 10. There's 10 times more noise than there is signal. Even in that case, you can identify pretty much the single peak. So this is fully reducible uncertainty. Now, let me make this a little bit more interesting. Let me consider a two-state Markov switching process where we're going to switch back and forth between two different spring constants. So it's as if we have two different springs going on, but you don't know which one you're looking at any point in time. So with this kind of a regime switching process, and if you don't know what the parameters are, now the question is, can you tell? Can you tell what's going on? It's a little bit more difficult. It depends. It depends on how you calibrate the parameters. So let me give you three different calibrations that I think will get the point across as to what we mean by partially reducible uncertainty. In one case, I'm going to assume that the switching across the two regimes is relatively few and far between. So you're in a state for a period of time, and then you switch, and then you stay in that state for a while, and then you switch back, and so on. So the switching happens relatively rarely. Okay? In that case, you get a displacement that looks like the upper left panel. You get high-frequency oscillations for one spring, relatively low-frequency oscillations for the other spring, and you can sort of tell when that regime switch occurs. The second case that I want to show you is the bottom calibration. The bottom calibration is where the regime switching is very rapid. So you're switching almost all the time between the two. And in that case, it sort of looks messy, but you can't tell that there are two different regimes. In fact, it sort of looks like one regime, doesn't it? And the middle case is the case where the regime switching is in between. It is neither fast nor slow as defined relative to the sampling interval and the number of data points that you have. So now, with those three different calibrations, let's try to look at what happens when you apply the standard fast Fourier transform. When you do that, look what happens. In the top right panel, where the regime switches happen slowly, you have two peaks. You can identify that you've got two springs going on. In the bottom panel, when the regime switching is happening so fast, you've basically got one peak, which happens to be the harmonic average of the frequencies of the two. You basically have effectively one spring. That is the average of the two. The middle panel is a mess. This looks like economics. And in a minute, I'll back that up. In the middle panel, it is virtually impossible to tell anything because the system is not stable enough in any meaningful way relative to your sampling interval and the horizon of the data that you've got. That's partially reducible uncertainty. And the point of this example is that physics and finance are not so different in terms of approach or objective. They're different in terms of the fundamental drivers of uncertainty that we deal with. In other words, if Hooke were trying to deal with a system like the middle, I doubt he would have come up with F equal minus kx. Or if Newton were dealing with gravity that changed every few weeks, I don't think he would have come up with F equal ma. The fact is that physicists have a much easier task in the sense that their laws, their relationships that have now come to be known as laws, their relationships have been stable for roughly the last 13.7 billion years. Right? A few minutes after the Big Bang, F did equal ma. And it stayed that way. So we're dealing with laws that change depending on all sorts of things, including the mood of Congress. So that's the challenge that we have. In fact, let me show you data. This is GDP data from the US in post-war periods. And the fast Fourier transform that I was referring to is the lower right. It actually looks a bit like the middle case from the previous slide. It is very difficult to capture partially reducible uncertainty simply because of the nature of the phenomenon. Even in a physical system, if we calibrate the parameters in such a way so that we simply cannot observe stable relationships over a period of time with the appropriate sampling, we will not be able to develop the same degree of precision that we are used to in physics. And in fact, there's a very specific example of totally reducible uncertainty that those of you who are signal processing experts will know exactly what I mean when I talk about the aliasing problem. There are certain identification issues that we will never be able to solve given a certain kind of data that we have. For those of you who are economists, the equivalent of the aliasing problem is supply and demand. If all I were to give you were price-quantity pairs that were the result of equilibration of supply and demand, if that's the only data that I gave you, and I gave you 1 million of these data points, and I asked you to tell me how to predict the impact of a 10% securities transactions tax on volume on the NYSE, you would never in 1 million years be able to figure it out unless you understood the basic principles of supply and demand. And once you did, you can figure it out with about 25 data points. So this highlights another interesting aspect of uncertainty, which is that whether or not a phenomenon is totally reducible or partially reducible or irreducible, it's not hardwired into that phenomenon, but rather it's a function of how smart we are in coming up with models to explain that phenomenon. So things that at one point look like totally irreducible uncertainty are today completely certain. And in the paper, we give a very simple example of this. 2,000 years ago, when people observed the total eclipse of the sun, that was considered an extraordinarily important, momentous, portentous event. And nobody understood anything about what was going on. Today, we can predict them to the millisecond when they will next occur. And that's an example of something that started out as a mystical form of totally irreducible uncertainty to something that today is completely certain. In the space of 2,000 years, we got smarter and we figured it out. Now, getting smarter is really what it's all about. And I'm going to argue that this taxonomy of uncertainty, as stylized as it may sound, actually has some pretty powerful applications. For example, I'm going to argue that the entire spectrum of knowledge can be arrayed according to the kind of uncertainty that the discipline is faced with. So, starting with mathematics at the very top, dealing with complete certainty, down to religion, which is designed to deal with irreducible uncertainty, all of the different academic disciplines are arrayed along this spectrum because of the nature of the underlying phenomenon that they grapple with. And economics is somewhere between biology and history. The problem comes when we think that it actually is at a different level. And so, from our perspective, problems with quantitative models and their applications really come about just for this reason. It's that we mistakenly apply a different level of uncertainty to the underlying phenomenon that we think we're modeling. Now, I realize this sounds like motherhood and apple pie, and what do you do with it in the end? And so in the paper, we really strain to try to come up with some actual practical implications. And the most practical of those implications, we think, can be summarized in what we call the uncertainty checklist. And I know it sounds a bit cheesy, particularly to a quantitative audience, to have these checklists. It sounds more like a self-help kind of a tool, right? And in particular, those of you who are quantitatively predisposed, you'll bristle at the idea of having to fill out these kinds of qualitative types of surveys. That's actually the point. What we want to do is to frustrate, annoy, disturb, and otherwise change the way you think about uncertainty, because only when you start getting some kind of cognitive dissonance between what you know and what you think you know, only then are you going to start understanding the limits of some of these ideas. So let me give you an example of this. In the paper, we actually go through this in much more detail, but the idea behind the uncertainty checklist is that for any practical setting, whether it's risk management or developing a new strategy or creating a new business, we suggest filling out this checklist for yourself as well as for colleagues that you're going to be partnering with for this venture. And the uncertainty checklist is organized as a table where you've got columns that involve the different kinds of uncertainty, level 1 through level 5. And the rows correspond to various different components of your business or strategy or particular task at hand. And the idea behind the checklist is to force yourself to identify parts of those businesses that are relevant for the different levels of uncertainty. So this is an example that we filled out for an equity market neutral strategy. That's what we described in the earlier part of the paper, where the various different components include the theoretical framework, the empirical analysis, the portfolio construction, trading implementation, and so on. And for each of these components of the business, you should force yourself to figure out what falls into level 1, level 2, level 3, and so on. So for example, for statistical arbitrage, level 1, basic mean reversion is really what you're trying to exploit. And level 2 is the stochastic process, say in AR1, that you might use to generate the theoretical mean, standard deviation, skewness, kurtosis, maximum drawdown, and other P&L statistics for your strategy. And level 3 may be the econometric estimators that you apply to try to get those parameters calibrated properly. And level 4 is what? What's level 4 for the theoretical framework? Other factors that you may not have incorporated, fear, greed, regulatory intervention, and so on. And level 5 is, well, you can imagine what level 5 might be. The point is that you may not have a very good answer for this checklist, but the point is not to come up with perfect answers. The point is to force you to ask the questions. Now, you'll notice that one of the levels at the very bottom is legal and regulatory issues. And that's a level that most quants never, ever have to deal with. And that's a mistake. Because as we've seen from the last couple of years, legal and regulatory issues have extraordinarily important impact on businesses. And this checklist will force you to grapple with them. Now, by the way, you'll find that it's interesting, the way I've arrayed these different components of the business, the bottom components tend to be more heavily weighted towards level 5, and the more theoretical and quantitative components at the top are more geared towards level 1. That's not by accident. The reason I did that is to illustrate the fact that most of us quants are much more comfortable being in the upper right quadrant here. Most of the business issues end up being in the, upper left, and most of the business issues end up being in the lower right. And that can be a real disconnect, especially if there are two different groups of people focusing on those different parts of the uncertainty checklist. In particular, if senior management is focusing on the lower right and the portfolio managers are focusing on the upper left and they don't talk, that can lead to real problems. I'll give you one illustration of this that I actually came upon quite by accident yesterday at a wonderful conference hosted by the NBER here in New York. At this conference, there were two economists that put together an interesting corporate governance index to measure the effectiveness of risk management in bank holding companies. So they picked a sample of something like 400 bank holding companies. I don't think they included the very largest of the banks because of access to data, but they had quite a significant sample of sort of mid-sized commercial banks. But at the level of the bank holding company, they were actually able to get a lot of information about various corporate governance aspects, like what the chief risk officer was paid, what the CEO was paid. They took the ratio of the two. I hope that they measure that in double precision because I'm sure it's a small number. But they were able to measure that. They were able to measure the number of independent directors and all sorts of things. And they came up with really interesting evidence about the degree of proper risk controls in various bank holding companies. And one statistic just stuck out to me like a sore thumb. It was really extraordinary. And the statistic was this. In their sample, 77% of the bank holding companies that they looked at had risk committees where none of the outside directors had any risk management experience. 77% of bank holding companies' external directors do not have any risk management experience. Think about what that means for the quality of risk management. So lower right, upper left. The point of this is that even for quants, we need to know about all of the cells in this uncertainty checklist. And while this won't give you any answers, it will force you to ask questions. And if you know that you don't know, that's actually a pretty important fact. Someone once said that there are people, those who know, but those who don't know, many of them don't know that they don't know. And that's a problem. So at least with a checklist like this, there's a chance that you might know you don't know. So let me summarize by saying that physics envy can in fact be hazardous to your wealth. And of course, it's the consequence of assuming incorrect levels of uncertainty. There are multiple levels that apply at any one point in time, of course, to any business or situation. And moreover, you need to include all of them in your analysis, not just focus on one or two. But you have to recognize that as knowledge accrues, you can move from one level of uncertainty to another, but you can also revert in situations where knowledge leaves an organization. It's often been said recently that what happened at AIG, part of what happened was a lot of the talent that existed in the early part of the organization of AIG Financial Products left the organization because they all retired, made enough money, and the folks that were left may not have been as experienced. Who knows whether that's true or false, but certainly you all are familiar with the phenomenon of people leaving the organization and not having their expertise at hand. Ultimately, the question about how you deal with physics envy is not to reject physics, it's not to reject quantitative methods, but rather to try to get smarter and to understand where our uncertainties are. And I think that all of this was really summarized very well in one simple sentence by the well-known physicist Richard Feynman. Shortly after October 87 stock market crash, Feynman was asked to speak to the graduating class of physics students at Caltech, and he thought about commenting on the financial crisis at that time by saying that they were all very fortunate to be studying physics, and he summarized it by saying, can you imagine how hard physics would be if electrons had feelings? And I think that summarizes the idea behind physics envy. Thank you. We have time for some questions, I think. Yes.
Hi, Andy. We both had Fisher Black. They know you. I had Brealey and Myers in 1982 with Bob Merton. Denial is not just a river in Egypt. And these facts that you're telling us are well known and have been well known for many years. I mean, I was a social studies concentrator at Harvard, and when Fisher and Bob were telling me this stuff, it was quite clear that they were not taking any of these things into account. Asset bubbles, the word asset bubbles, we're currently on the 10th edition of Brealey and Myers. The term asset bubble doesn't even appear through edition 8. Okay, that's something like 25 years. Okay, Schiller's papers are in 81. So, not only was the profession seems to have been in active denial of these issues. I applaud you bringing them up and starting to talk about them here. But these are very obvious things that are obvious to any student who has any social history background. Many people say there shouldn't be a Nobel Prize in economics because it's not a science. So my question to you, since you're much more academically in the field than me, is why has there been such a delay? Why has there been such a denial? Why has Samuelson's reservations, Keynes's reservations, Fisher's reservations, who we both experienced personally, why has this been basically not in evidence?
Well, so that's a great question, and I have a couple of answers. I'm not sure I have the answer because I think it's complex, and it really goes to the sociology of science or sociology of academics.
It's a Thomas Kuhn structure of scientific revolution, but that was available in 1960.
Right. But Samuelson, I think, put it best when he said that progress in the sciences occurs funeral by funeral. It occurs very slowly.
Yeah, well, my brother-in-law professor at Chicago said he got tenure because enough people died.
Right.
Okay, that's not a good system.
You're
Maybe
right.
tenure should be abolished.
Well, that's a separate discussion that I'm happy to have. And actually, I have had it. To your point, I actually made that comment once at a faculty meeting of various different departmental faculty members. I was invited to this dinner by the provost shortly after I got tenure. And one of the other faculty members was leaving MIT to go to Oxford. And as you may know, in the UK, they abolished tenure. So you don't have tenure if you go to Oxford. So I said to this philosophy professor, I see that you've decided to give up tenure. And he said, well, yeah, I suppose that's right. And so I commented on the fact that I thought that was a great thing and that we ought to get rid of tenure because it creates a certain degree of entrenched, ideas and people that, end up slowing down progress. At which point, an old, wizened professor from the back of the room came over, walking on a cane, and said to me, pointing a crooked finger, he said that, Professor Lowe, I was here at MIT in the 1940s and 50s during the McCarthy era when they were persecuting people that had ideas different from the rest. And I can tell you that tenure is an incredibly valuable thing during exactly
Mr. McCarthy's a bad guy and he went away. That's a stale argument.
Well, nevertheless, it is a compelling one at the point at which he made it, because I shut up pretty quickly. And there is this notion of academic freedom allowing individuals, including myself, to say things that are unpopular. And frankly, a paper like this, I couldn't have written before I got tenure. So that's one example. But I have a better answer. That's not enough. I think that the predominant theory of efficient markets has become so widespread because what came before it was so bad. And it provided us with an incredibly powerful framework for thinking through issues in a tremendously systematic way. And frankly, markets are mostly efficient most of the time, but it's the exceptions that strike us as being both interesting and, from a practitioner's point of view, extraordinarily important for building businesses.
It's a great first-order approximation, no question.
That's right. And as with academics, we need to focus on that first-order approximation to the point perhaps beyond diminishing marginal return. And now we've gotten to that point, and hopefully, with enough funerals, we're going to move on to the next set of ideas. But I take your point, and I agree very much with the spirit of it. Yes.
Yeah. Despite the fact I brought my slide rule and my pockets full of pens, and I've been using math in this industry for 3 decades, I know I'm not an engineer. And I dare say I know people who are engineers. Some of my best friends are engineers, and I don't think there are any engineers in the world of financial engineering. Engineers don't build bridges that collapse all the time, that they don't build these well, sometimes they do, but not all the time. And they're ashamed of it, and they study it.
Yeah.
And, Tacoma Narrows is an example of what not to do.
Yeah.
And we seem to apologize for those things. Well, I'm sorry, we don't apologize for those things.
Yeah.
So thank you for the history of how it came to be people started to think economics might look like like physics, but how could it possibly be? And there are engineering schools that have financial engineering departments. How come the other engineers don't say, what are you doing to our name?
Yeah. So I have a lot of sympathy with that set of sentiments, but I want to expound on that a little bit, if you don't mind. One thing you said really struck me, and I think it's at the core of good engineering. Engineers are not perfect. Bridges do collapse, space shuttles do blow up, and nuclear power plants do melt down. But engineers do something after it. What they do is they study their failures. They figure out what went wrong, and they get smarter about it. And I think we need to do that too.
Absolutely.
But I don't think we do now. And I don't think it's necessarily just the fault of the financial engineers. I actually do think a lot of financial engineers, people in this room, care a great deal about what happened. In fact, you're going to hear this afternoon from financial engineers like John Hull and Dick Roll, who will tell you what they think, what went wrong, and what didn't go wrong. They're going to study the data, and they're going to go through analysis. But that's not enough. We need to have the same ethic across the entire industry and in government that we have in engineering. For example, when an airplane goes down, what happens? We get the National Transportation Safety Board. They come on the scene, collect the black box, sift through the wreckage, and in a year or so, they produce a report, a conclusive report that tells you what happened, how it happened, why it happened, and what needs to happen in order to make sure it doesn't happen again. There's no politics. These kinds of teams, the GO teams that are from the NTSB, these are engineers from Boeing, from Airbus, from all over the country that are on assignment for 6 months to a year from their companies that end up going through the wreckage in order to figure out what happened. What do we have? We have a bipartisan commission, the Financial Crisis Inquiry Commission, that actually hasn't even finished its report, and already we're about to pass bills about how to fix the financial system. That seems to me a little bit backwards, right? Isn't it like fire, ready, aim? I mean, so I couldn't agree with you more.
Absolutely. This should be the association of people who aspire to someday become engineers.
Yeah.
All the engineers I know do it for the betterment of mankind. Almost everybody I know in this industry talks about greed
Yeah. Well,
as a motivator. And it's
So-
true, but it's only explanation. It isn't
well,
what
I
it's
would
supposed to become.
I would take issue with that a little bit. I have to say, you're right that obviously money is the metric by which we measure financial success. I mean, just because of that's sort of the convenient metric, right? It's P&L. We all think in those terms. But I have to say that of the people that I've met at various different financial institutions, most of them are actually not motivated by money. In fact, most of them have made more money than they will ever be able to spend for their entire lives, and actually spend a lot of time giving it away. They're motivated by the same thing that engineers are motivated by, which is ego, as well as, in some cases, a desire to do good. And I really believe that. Now, the chairman of Intel is not focused on doing good. The chairman of Intel is focused on making profits for his shareholders and doing something really cool along the same lines. I think that we have that same ethic developing, but we are at a different point in our field.
By the way, you've made the kind of point I'm making. Our theory
Yeah.
is based on greed, not by these other motivations.
Yeah, that's right. And I think that we need to ultimately become more like engineers in the ethic that they apply and the standards that they use. Part of it has to do with the discipline. Our field is not nearly as precise as most areas of engineering, but there are some areas of engineering that are not that different, frankly. So I think we can learn a lot. And frankly, at MIT, we have the benefit of a lot of colleagues in our engineering school that are now taking an interest in finance. We welcome that. In fact, a number of my students here are students from the School of Engineering, and they've made tremendous progress and impact on the industry over time. I think that's going to help. But there's something that has to happen at the very highest levels of government. We need to take this more seriously.
Thank you for your insight and wisdom, and most importantly, passion.
Thank you. Yes.
About the table that you showed about taxonomy of uncertainty,
Yeah.
on the risk management row, don't you think we can add the uncertainty of human interactions or like behavioral?
Yes, absolutely. That is definitely, that should be in there. And more we are understanding a lot about human behavior that we didn't maybe even just 10 years ago. And I think taking that more seriously is definitely a key aspect of risk management. In fact, it's a key aspect of all of these things. For example, remember what happened in 2008, after, with all of what's going on with Bear Stearns and Lehman Brothers, Congress decided to suspend short sales. Now, if you're an equity market neutral trader, now what do? You can't short half your book. Okay, well, I guess you're out of business. So that's an example of a reaction to human behavior. Gee, a lot of stocks are going down. We don't like that. Let's not let them go down. Let's legislate away losses. That's human behavior. And the biggest source of uncertainty today happens to be government intervention. So absolutely, that belongs in there.
Thanks.
Yes.
I guess what progress has been made on complexity theory? I mean, stuff like self-organized criticality, etc. Their role in finance seems to be a little more limited than.
It is. I actually know a little bit about the history of it because when this stuff started percolating through, maybe 2 decades ago, I got interested in it. In nonlinear dynamical systems, I think was the term at that time. Then it became chaos theory, and then it became complexity theory, and there's lots of different buzzwords for it. But the Santa Fe Institute is sort of a good nexus for a lot of these ideas. Doan Farmer has been a tremendous asset to the literature because not only is he a physicist, but he also ran a hedge fund quite successfully for many years, so he understands both sides of the fence. And so there has been some progress, but I think the progress is slower, again, because of the nature of the uncertainty in finance. For example, if you were to do Poincare sections to try to deduce what the dimensionality is of the data or of the financial data that you're trying to model, you find that with any kind of measure of dimension, whether it's the correlation dimension, you get something like 15 to 20 dimensions that you need. Now, typically for these kinds of dynamical systems, if you do 2 or 3 dimensions, you can actually do these kind of Poincare sections to recover the dynamics. With 15 or 20 dimensions, forget it. I mean, it just you can't even simulate that system. It's so complex. So it seems like it's the nature of the beast, but as we learn more and more about how to model, we may end up becoming a little bit better at that.
So does that mean that we're ultimately bound by the hardware we use, specifically the computer hardware?
Yeah, we are. We're bound by the resources that we use, including hardware, but probably hardware and software are important. I think the biggest limitation is wetware. That is, what's up here. And the more people we have, the more smart people we have, the more engineers we have looking at this problem, the better off we'll be. To give you one simple example of that, and to get back to the point about financial engineering and how we are or are not like engineers, in 2007, the MIT School of Engineering graduated 337 PhDs in engineering. 337 PhDs in engineering. That same year, the MIT Sloan School of Management, we produced 4 PhDs in financial engineering. Now, of those 337 PhDs in engineering, how many of you do you think were paid for by government grants? 337. That's right. Of the 4 PhDs in finance, how many do you think were paid for by government grants? None. There are none. There are no government grants for financial engineering. So is it any wonder that we have the financial system that we do? We don't support it. We don't support it. There aren't enough smart people looking at the problem. And by the way, if you're an engineer, what's the one thing you enjoy above anything else? It's figuring out a problem with the system, finding a mistake, demonstrating that you know better, and here's how to do it. Imagine having 10,000 people focusing on these kinds of issues every day versus 1,000. You're going to find much, much quicker improvements with more people looking at these issues. We don't have enough people focusing on financial engineering. We need more. Yeah.
You mentioned that the physics and finance have the same approach but the different level of uncertainty. What about the fact that actually your financial model can modify the problem that your model describes? For example, as I've heard, I don't know if it's correct or not, but when Black and Scholes developed their model was fitting much less at that time than it would fit now, because everybody is using it.
Well, that's just it. That's one of the examples of irreducible or partially reducible uncertainty. And this is goes to Richard Feynman's comment about if electrons had feelings. The fact is that our actions and our theories and our implementation actually affects the system directly in a much deeper way and in a much more direct way than Heisenberg's uncertainty principle. I mean, it's a little bit like Heisenberg's uncertainty principle, but it's worse in the sense that it happens all the time with all the phenomena that we try to engage in, depending on the nature of the assets under management, depending on what day of the week it is, and so on. So that's an additional source of complexity that we have to build into our models. I believe we can do that. I think that there are methods for us to figure out not only what the right answer is, but what happens when we actually implement the right answer and everybody else has the wrong answer and eventually they figure it out. There is a mechanism for calculating that kind of feedback loop. It's not perfect, but it's part of the science and it's part of how we get better at this. Yes. Oh, sorry. Here and over there.
I wonder if I could challenge that just a little bit in the sense that, I think you've yourself pointed out during the course of the talk that there are certain aspects of risk that are not knowable. So I don't know whether actually unleashing more engineers on the problem would necessarily solve those. Because, for example, since finance is largely a human endeavor, the system you're studying each time is different. If,
Yeah.
for example, you've just passed legislation to change the system,
Yeah.
and we also happen to have very large, greedy institutions that
Yes.
we've created in this process, and they create systemic risks.
Yes.
I mean, to the extent that risks are small, individual risks,
Yeah.
I mean, you can rely on the general goodness of people as well as on the canceling out of a lot of countervailing individual actions. But large institutions that are greedy are also often stupid because they are conglomerates of people and not necessarily people, so they have very sort of singular objectives,
Yes.
and they tend to pursue them to the
Yeah.
detriment of everybody else.
Yeah.
So, and the moment that you create regulations to,
Yes.
to stop them, the market finds a way around those.
Yeah.
So I wonder whether, in fact, these problems are solvable with more engineers.
Well, let me put it this way. My response is that we have two choices. We can either study the problem harder and try to get smarter, or we can ignore the problem and hope it goes away. I don't see any other choice, right? Those are the two possibilities. And so if you ask me, I'm biased, I'm always going to choose to get smarter. And I do believe that the challenges that you mentioned are challenges that we can overcome with better models, more responsive models, and a broader set of models that take into account, frankly, legislative oversight and the dynamics of regulatory shifts. To give you an example, we had regulations in place to deal with this issue, the Glass-Steagall Act. Moreover, we had regulations in place to deal with the behavior of mortgage brokers that ended up giving out liar loans and ninja loans and all that. It's right. We had the Investment Advisors Act. We had oversight. We chose not to enforce. The reason we didn't enforce them is because of human behavior. Human behavior allowed us to basically take the system and say, gee, it's fine now. We don't need these protections. Let's take them off. So that's an example of human behavior that we now know about. Well, if we know about it, don't you think we can get smarter about it? For example, sorry.
I'd like to think that.
Yeah.
I'm just a little more pessimistic than you are, I suppose.
Well, yes. So, I mean, I guess hope bleeds eternal. So I'm gonna continue to be hopeful. And I guess we're running out of time, so maybe the last question over there. Yeah. Can you press your button and?
You mentioned earlier that about how we need to one of the issues that seems to appear here is the people who are supposed to be smart often really are the ones who are missed on what happened in 2008, 2009, and in general, the people who found those theories are not really held that accountable. And some of these, Krugman often writes about it, about being acceptably wrong and all these things. But the issue, for example, when you're presenting what you're saying, you just presented on the example of the flip of the coin, or another flip of the coin, your example on making the draw. The solution that I understand you're proposing here in the case of uncertainties are maximum entropy. One of the issues that happened when it happened on the news when there was the crisis about how to put the assets out, that solution was put, but in practice, what happened is that the decision that people had to make was dependent on how much liquidity they had in their hand. It had nothing to do with the fact that when you are saying how much are you willing to put 1,000, 2,000, or 3,000 here, it really had nothing. It depended on if you have $1 billion, okay, you could put let's say 1,000 to play the game. If you had less than that, even $1 is not enough. So the issue here is that, and there are people who have made that type of argument, and it never went up. It never really was reflected in the discussions that were made. The only arguments that were put in place are just the type of arguments that come from physics and things like that. So one of the issues that when I hear you talking, is just that there are people who have who have better opinion, but because the level of uncertainty is so high here, it's very difficult to triage who is right really here and who is wrong. For example, here you might talk, okay, people will say, oh, he's a professor at MIT, so we'll give him credit for what he's saying, even if it may not be so good, or someone else will not have. That's really, I think, in finance, that really is a serious problem. And I mean, when there's so much uncertainty, people may use other means to get the thing. So that's really my comment here, and how, I mean, you will see about making sure that this does not happen, at least in finance law.
So I think that these are all valuable concerns that I don't think has easy answers, because you're talking about a much more general phenomenon of how can you guarantee that the right people are in charge at any point in time? And the answer is you can't. And the higher the level of uncertainty, the more difficult it is to understand whether or not performance is actually genuine or random. Frankly, that's the whole issue behind pay for performance. We don't have any problem with the fact that Tom Brady gets paid $25 million a year, because we can measure his performance in yardage, in completed passes, in gate receipts. We can measure his performance, and $25 million is a bargain for that contract. But when you have an individual that makes $100 million bonus because the individual happened to be at the right place at the right time with the right set of market conditions, it's a little bit harder to tell. It's not impossible, but it's harder. It's harder. So what you're saying, it's harder. The people that are in charge now, do they belong in charge, or should we get somebody else? Should we get, only people from MIT? That might be a good answer. We have, but I don't have an answer for you there, other than to say that the way that society evolves is through the process of selective trial and error. And the more chances we have of trying new things out and picking the very best of those ideas, the more likely we'll find and make genuine progress in all of this mess. And it applies to all fields, not just finance. Having this oil spill in the Gulf of Mexico seems amazing to me, how we can't stop it. Well, isn't that just a simple engineering problem? Well, apparently not. It's not so simple. And so that's an example of a very complex, challenging phenomenon that involves people. And anytime you get people involved, the dynamics become extraordinarily complex, partially reducible uncertainty. What we're hoping to accomplish in this very modest paper is to at least create a lexicon now for starting to talk about some of the disconnect between theory and practice. And over time, after enough funerals, the hope is that we'll actually make more progress. And with more and more people like this audience here to work on it, I'm actually very confident that we will make progress even in the next 5 or 10 years. Thank you very much.
I just want to say a quick thank you to Andy Lowe for coming today. And actually, this is a special IFE conference where we have 4 senior fellows, because Richard Bull will become a senior fellow as well in the tradition of the FEOI. So a couple of housekeeping notes. We are going to shorten our lunch a little bit so we get back on schedule. We will reconvene at 1:40 for lunch back in this, for the John Hall speech at 1:40 back in this room. Lunch will be served out where breakfast was, behind the glass wall. Take a lunch. We have a couple lunch rooms we'll be directing you to, but basically there's one this way and there's one this way. See you at 1:40. Thank you. No, that's fine.